Hi boys and girls, this is lecture 1.6 in Unit 1, the topic rational expressions. We start with the definition of a rational function. A rational function has the form f of x equals p of x over q of x, where p of x and q of x are polynomials. And q of x cannot be 0. Why? Because q of x is in the denominator of a fraction. As we all know, you can't have 0 in the denominator of a fraction. This leads to some interesting features on the graph of a rational function. The graph of the parent function, f of x equals 1 over x, is a hyperbola, a new shape, which consists of two symmetrical parts called branches. Notice a new feature of the graph is introduced, the asymptote. The vertical asymptote occurs where the denominator of the rational function equals 0. Look at this function 1 over x. P of x is 1, q of x is x. Where is this denominator going to be equal to 0? When x is equal to 0. So the vertical asymptote of this graph is right here where x is equal to 0, essentially the y-axis. This also has a horizontal asymptote. These simple rational functions will also not be equal to 0. So there's a horizontal asymptote at 0, a vertical asymptote at 0 as well. In general, the domain of a rational function includes all real numbers except for the vertical asymptotes, and the range of a rational function includes all real numbers except for the horizontal asymptote. Okay, now let's graph a couple of simple rational functions. We have some instructions here. To graph a simple rational function, first, draw the vertical and horizontal asymptotes of the function. Second, plot points on both sides of the vertical asymptote. Third, draw the branches of the hyperbola. We're going to graph the function y equals 6 over x. You can see this denominator is not defined where x equals 0 again. So the vertical asymptote of this function is also going to be 0. I'll draw it alongside the y-axis. Also notice that since this is a simple rational function, there's going to be a horizontal asymptote as well at 0. So once we've drawn the asymptotes, we're going to plot a few points on either side of the vertical asymptote. Since the vertical asymptote is occurring at 0, we know the function is undefined there. Let's choose a few points on either side, 1, 2, 3, and -1, -2, -3. We'll plug each x value into the function to generate the y value. 6 over 3 is 2. 6 over 2 is 3, and 6 over 1 is 6. -1 plugged in for x gives us 6 over -1, which is -6. 6 over -2 is going to be -3, and 6 over -3 is -2. Now let's plot these points. We have 1, 2, 3, 2, 2, 3, and 1, 6. So the right branch of this hyperbola is going to look like that. Then to the left of the vertical asymptote, we have -1, -6. We have -2, -3. We have -3, -2. So the left branch is going to look like that. And there you have the graph of a hyperbola. Now, let's look at some transformations of a simple rational function. Notice we have what we would expect to be a horizontal shift here and a vertical shift here, and that's exactly right. This is going to change the vertical asymptote from being 0 to being h, and the horizontal asymptote will be whatever k is. So let's look at an example like that. F of x equals -4 over x plus 2 minus 1. So remember, in a simple rational function, the vertical asymptote was at 0 and the horizontal asymptote was at 0. But with this horizontal shift, remember it's the opposite sign when it's a horizontal shift, we expect our vertical asymptote to now be shifted left 2 units to -2. And that makes sense because think, where will x plus 2 be equal to 0? At x equals -2. This is where the function is undefined. Therefore, that's where the vertical asymptote will be. The horizontal asymptote is going to be -1, indicating the vertical shift. Now, since the vertical asymptote is at -2, let that be in the center of your parabola. The function is undefined there. And then choose 3 points on either side of -2. Once again, plugging these x values into the function, we'll discover what function values or y values go with. If I put 1 in for x, I get negative 4 over 3 minus 1, which is negative 7/3. When I put 0 in, negative 4 over 2 is negative 2 minus 1, which is negative 3. And when I put negative 1 in, I get negative 4 over 1, which is negative 4, minus 1, negative 5. If I put negative 3 in, negative 3 plus 2 is negative 1. Negative 4 over negative 1 is positive 4, minus 1 is 3. And when I put negative 4 in, negative 4 plus 2 is negative 2. Negative 4 over negative 2 is positive 2, minus 1 is 1. And negative 5 plus 2 is a negative 3. Negative 4 over negative 3 is positive 4/3, minus 1 is 1/3. Let's plot these points. Remember, negative 7/3 is negative 2 and 1/3. So at 1, we are going to have 1, 2, negative 2 and 1/3. At 0, we have negative 3. And at negative 1, we're down here at negative 5. So here's the right branch of the hyperbola. And then on the other side of negative 2, at negative 3, we have positive 3. At negative 4, we have 1. And at negative 5, we have 1/3. So here is the left branch of the hyperbola. Notice that it is flipped over the axes. The 4 was negative, indicating a reflection. So we should not be surprised to see that transformation in our graph as well. Now let's graph general rational functions. We're moving from simple to more general graphs. We'll start with the form y equals ax plus b over cx plus d. The vertical asymptote of this graph is the line x equals negative d over c, because the function is undefined when the denominator, cx plus d, is equal to 0. If you set up an equation with cx plus d equals 0 and solved for x, you would get negative d over c. That's where the denominator equals 0, therefore that's where the function's undefined, therefore that's where the vertical asymptote will be on your graph. The horizontal asymptote is the line y equals a over c. That's the ratio of these leading coefficients. And so let's graph the function y equals 2x plus 1 over x minus 3, starting with finding the asymptotes. Where is this denominator equal to 0? X minus 3 is equal to 0 when x is equal to 3. Therefore, our vertical asymptote is going to be at 3. The horizontal asymptote will be the ratio of the leading coefficients, 2 over 1. That's at 2. And so there's the horizontal asymptote. Once we have the asymptotes drawn, we want to pick a few points on either side of the vertical asymptote. So we'll let 3 be the center of our table. We know the function's undefined there, but this indicates that we're going to look at 2, 1, and 0, 4, 5, and 6 to get enough points to graph the branches on either side of the vertical asymptote. When we put 0 into the function, we get negative 1/3 as the y value. When you put 1 into the function, 2 plus 1 is 3. 1 minus 3 is negative 2. That's negative 3/2. And putting 1 into the function, that's a 2. Yes, it looks like a 1, but it's supposed to be a 2. 2 into the function gives us 2 times 2 plus 1, 5, over 2 minus 3, negative 1. That's a negative 5. Now let's go to the other side of the asymptote. When we put 4 into the function, 2 times 4 is 8 plus 1 is 9, over 4 minus 3, 1, so that's going to be a 9. 5 times 2 is 10 plus 1 is 11, over 5 minus 3, 2, 11/2. And finally, let's put 6 into the function. That's 12 plus 1, 13, over 6 minus 3, 3 13/3. Let's plot these points. 0, negative 1/3, 1, negative 3/2, and 2, negative 5. So here is the left branch of the hyperbola. On the right side of the vertical asymptote, we have 4, 9. We have 5 11/2, which is about 5.5. And we have 6 13/3, that's 4 1/3, which is about right here. Here's the right branch of the hyperbola. All right, now let's move on to the second example. We're going to graph a function of the form p of x over q of x. Of course, that's just the general form of a rational function. But basically now, any degree polynomial over any degree polynomial in the denominator. If p of x and q of x are polynomials with degree m, that's for p of x, and n, that's for q of x, respectively, Vertical asymptotes occur where q of x equals 0. That hasn't changed. Where this denominator equals 0 is where we're going to have our vertical asymptotes. However, this gets a little bit more complex as far as determining horizontal asymptotes. There is at most one horizontal asymptote. It's determined by the degrees of p of x and q of x. Now remember, m and n represent the degrees of polynomials p of x and q of x. When m is less than n, that means the degree of p of x is less than the degree of q of x. 0 is the horizontal asymptote. When m equals n, that means the degree of p of x is the same as the degree of q of x. The ratio of the leading coefficients is the horizontal asymptote. That's the situation we had here. This is degree 1 and this is degree 1. When it's the same, you take the ratio of the leading coefficients. And our last case will be when m is greater than n, that is the degree of p of x is greater than the degree of q of x, there are no horizontal asymptotes. So let's find the vertical asymptotes of this function by setting the denominator equal to 0. X squared minus 9 equals 0 yields two places where the denominator is equal to 0 at plus or minus 3. Therefore, this particular function is going to have two vertical asymptotes, one at negative 3 and one at positive 3. Hopefully your lines will not be so wavy. They will be more vertical. Now, where is the horizontal asymptote? That depends on the degree of the numerator and the degree of the denominator. Since they're both degree 2, this takes us to the second case, m equals n, which means the horizontal asymptote will be the ratio of the leading coefficients, 2 over 1. A horizontal asymptote, therefore, is going to be at 2. Now that the asymptotes are drawn, let's get some points so we can plot the branches of this hyperbola. Now, with two vertical asymptotes, things are a little bit more complicated. We need a few points in here. We want all of the values in here. We want a few points here as well. So I'm going to get negative 6, negative 5, negative 4. Of course, negative 3 we know is undefined. We're going to look at negative 2, negative 1, 0, and notice I have a double table of values here. 1, 2, of course 3 is also undefined, and then we're going to want a few points on the other side of 3 as well. All of these values must be found. Well, given the complexity of this graph, I'm going to bring out our old friend TI-84. Notice that I've already plugged in this function, and when I graph it, I see the hyperbola that I am trying to construct. But more interesting to me, of course, is the table of values. I need to go back and look at negative 6, and don't be afraid of some decimals here. We might as well not be afraid of them because that's what we're going to graph. We have 2.7 here. Negative 5 gives us 3.125. I'll just say 3.1. Negative 4 is about 4.6. Not surprisingly, negative 3 is undefined. Now let's look at the numbers between negative 2 and negative 3. Oops, I went too far. Going back to negative 2, I'm going to have negative 1.6. For negative 1, negative 0.25. 0 gives me 0. 1 gives me negative 0.25 again. 2 is negative 1.6. 1.6, and then on the other side of the asymptote I have 4.6 again. I'm expecting that same symmetry, and so let's go down and take a look at 5 and 6 just to be on the safe side. We have 3.1 for 5, and we have for 6 2.7, just like we expected. Now of course that was helpful. Thank you, TI-84. Now let's plot these points. We have negative 6 is 2.7, which is about right here. We have negative 5 is 3.1, which is about right here. And negative 4 is 4.6, which is approximately here. Here's this branch. On the inside of the two vertical asymptotes, we have negative 2, negative 1.6, negative 1, negative 0.25, 0, 0, another negative 0.25 at 1, and then 2 gives us negative 1.6 again. Here is the branch on the inside of the two asymptotes, and on the other side we have 4 is going to be 4.6, which is approximately here. We have 5 is 3.1, which is about right there, and 6 is 2.7, which is about right here. Our last branch. And there we have it. We have done a lot of graphing of rational functions, but I think we know exactly what to do. This little section in here is very important for what we're going to be doing in calculus, so make sure you understand how to get these horizontal asymptotes based on those three cases. Okay, now we segue from graphing to operations with rational functions and expressions. Starting with simplifying. Simplifying a rational expression usually requires two steps. Factor the numerator and denominator, and divide out any factors that are common to both the numerator and denominator. Since rational expressions are fractions, this is akin to reducing a fraction, but it requires that we factor everything first. So here's an example. We factored this numerator by taking out an x. Of course, rewriting x squared as x times x. That means we were able to cancel these x's, and here's the reduced form of the answer. These x's cannot be canceled. You can only cancel something in the numerator and denominator if it's a factor multiplied by something else. When it's added or subtracted to something, it cannot be canceled with anything in any part of the fraction. So when multiplying and dividing rational expressions, we're going to factor each expression first, then cancel common factors, then apply rules for multiplying and dividing fractions. So first we're going to multiply these two rational expressions. I rewrote it down here so I can do some factoring. When I factor this numerator, I'm going to have x plus 4, x minus 1. That's the new numerator in factored form. Factoring this denominator gives me x plus 2, x plus 2. Now let's move to the second rational expression. I can take out a 2x, and then that leaves x plus 2. And then this denominator becomes x minus 3, x minus 1. Now that everything's fully factored, we look for anything that we can cancel, any numerator term with any denominator term. So I can cancel this, and I'm left with, in the numerator, a 2x and an x plus 4. I'll write it down here. And in the denominator, an x plus 2 and an x minus 3. No need to refoil all of this. Just leave your answer in factored form, and that's how it's done. Dividing is very similar, but of course we have to flip the second fraction first. So I'm going to rewrite this, x squared minus 6x minus 27 over 2x squared plus 2x, and then times x squared over x squared minus 14x plus 45. We cannot forget that dividing is actually multiplying by the reciprocal of the second fraction. Now let's do our factoring. This becomes x minus 9, x plus 3. That's that new numerator. Here we can just take out a GCF, and this leaves x plus 1. Over here, x squared cannot really be factored any further, so we leave that alone. And this becomes x minus 9, x minus 5. That's that new denominator. The x minus 9's cancel, and that's all. Well, actually, this x can cancel with these two, leaving 1 in the numerator. So our new numerator is x plus 3, and our new denominator is x plus 1, and then x minus 5. And that's how you multiply and divide rational expressions. Now, when adding and subtracting rational expressions, we're going to have to find a common denominator, just as you would if you were adding and subtracting fractions. But we will not be able to find a common denominator until we factor everything in our denominators first. So I'm going to rewrite this denominator, factoring out a 3x, and then that leaves an x plus 1. Now, our common denominator will consist of every single type of factor that we see in our denominators. A type of factor we have here is 3 to the 1 and 3 squared. We need the largest of that kind, which means we're going to need 3 squared or 9 in our common denominator. We have an x to the 1 and an x squared. We need the largest of that kind of factor, which means we need the x squared, and of course we need the x plus 1 as well. This is our common denominator. Now let's see how each numerator must be changed accordingly. This fraction needs to be multiplied by x plus 1 over x plus 1 for the current denominator to now match the new denominator. That means this numerator is going to change to 7 times x plus 1. This fraction is going to need to be multiplied by a 3x over 3x. It has the x plus 1, it has one of the x's and one of the 3's, but needs another 3 and another x to match the new denominator. So this numerator is going to be x times 3x. Now let's simplify this numerator. This becomes 7x plus 7 plus 3x squared. We look for any like terms and combine them if we can, but as you can see, in this case, there are no like terms. If I want to, I can rearrange this in descending order. 3x squared plus 7x plus 7 over 9x squared x plus 1. And now we have added these two fractions together. Let's try subtracting. Of course, it's going to be very similar. Let's factor these denominators. This becomes 2 times x minus 1. And this denominator factors into x minus 1, x minus 3. All right, so in constructing our new denominator, I'll need the 2. I'll need the x minus 1. And I'll also need the x minus 3. Now, how does each fraction have to change in order to match this new denominator? This fraction will need to be multiplied by x minus 3 over x minus 3. Notice it already had the 2 and the x minus 1, therefore x minus 3 is the only factor it's missing. This numerator is just going to have to be multiplied by the 2 over 2 because it already has the x minus 1 and the x minus 3. So that's going to give me an x minus 3 times an x plus 2 here. And then minus, I need to be careful with that negative, a negative 2x minus 1 times a 2. In simplifying, I'm going to FOIL out these terms. I get x squared minus plus 2x minus 3x is minus x and then minus 6. And then let's think of this as a negative 2 multiplied by a negative 2x. That's a positive 4x. A negative 2 times a negative 1 is a positive 2. There's our numerator. And let's see if we have any like terms. Don't FOIL out your denominator. You never know, sometimes the numerator might become something that can be factored and canceled with one of the factors in your numerator. So you leave it in factored form just in case. My new numerator, x squared, has no like terms, but I can add negative x and 4x and get a positive 3x. I can add a negative 6 and a positive 2 and get a negative 4. And that's over, of course, 2x minus 1 and then x minus 3. Now notice this can be factored into x plus 4, x minus 1, which is exciting because we have an x minus 1 factor in the denominator. Thank goodness we didn't FOIL the denominator, because now we can cancel those factors, leaving our most simplified form of the answer to be x plus 4 over 2 quantity x minus 3. And that's how you add and subtract rational expressions. One final operation we're going to look at with rational expressions is simplifying complex fractions. A complex fraction is a fraction that contains a fraction in the numerator and or denominator of a fraction. So it can be a fraction with just a fraction in the numerator or just a fraction in the denominator, or as in this case, fractions in both. The easiest way to simplify this, although there is more than one method, I'm just going to show you the one method, which is what is the common denominator of all the denominators that you see. You can see that it's an x and an x plus 4. We're going to multiply the numerator times x, x plus 4, and the denominator times x, x plus 4. In doing so, we're going to, in one fell swoop, eliminate all of the denominators. Notice what happens in the numerator. 3 over x plus 4 times x, x plus 4 over 1, you can think of it that way, cancels these x plus 4's, leaving just 3 times x in this numerator. In this denominator, we're going to distribute x, x plus 4 to the first fraction, which cancels the x plus 4, leaving an x times the 1, which is x. And then we distribute it to the second term, and the x's cancel, leaving 2 times x plus 4. So this becomes plus 2 times x plus 4. This quickly simplifies to 3x over x plus 2x plus 8, which results in 3x over 3x plus 8. Not so complicated after all, right, boys and girls? All right, on to our last topic. Solving rational equations. Since an equal sign has now been dropped into the expressions, we are no longer going to get some sort of simplified rational expression as our answer. Rather, we're going to get a value, or perhaps more than one number, which will be the solutions to the equation. Before we begin, however, we need to take a look at these denominators and understand that because they are fractions, and because we cannot ever let these denominators be zero, we have to exclude values that will make this happen. Notice that as we look at this denominator, we can say x can never be -1. In fact, as we look at this denominator, we can also say x can never be -5/4. These automatically are excluded from the domain of this equation and cannot be considered as possible answers because we can never have a situation which makes a denominator equal to 0. Now let's get back to solving the equation. Since this is a single fraction equal to a single fraction, I hope you recognize this as a proportion. We can solve it by cross multiplying. This will be 3 times 4x plus 5. And that's going to equal 9 times x plus 1. In distributing, we get 12x plus 15. On the right side, 9x plus 9. Let's subtract the 9x over and get 3x, and then subtract the 15 to get -6. X is equal to -2. Now, thankfully, it's not one of the numbers that were automatically excluded from this domain, but we should check it anyway because occasionally you do get extraneous solutions. -2 plus 1 is -1. 3 over -1 is -3. 4 times -2 is -8, plus 5 is -3. 9 over -3 is also -3. Since -3 does equal -3, -2 is a valid solution. Now let's move on to letter B. Once again, let's look at these denominators, and I'll factor this one, and determine what values must be excluded from the domain, from any possibility of being a solution. As you can see, x can never be equal to 3, and x can never be equal to -3. That just has to be something that we make a note of right away. Now, going back to solving the equation, we can see that it's not a proportion. It's not a single fraction equal to a single fraction. In fact, one way of solving it would be to combine these two into one single fraction and then cross multiply, but that's not the method I'm going to use. Rather, I'm going to once again look at all of the denominators, find the common denominator, and multiply that by each of the terms. Since the common denominator is x minus 3, x plus 3, I'm going to multiply each term in this problem by that common denominator. In doing so, all of the current denominators will cancel out, leaving a much easier equation to solve. And finally, x minus 3, x plus 3 to this term. Now notice what cancels. In the first term, the x minus 3's cancel, leaving 6 times x plus 3 on the left side of the equation. On the right side, the entire denominator cancels out, just leaving 8x squared. And for this last term, the x plus 3 cancels, leaving a -4x times the quantity x minus 3. Let's distribute. We end up with 6x plus 18. On the right side of the equation, we end up with 8x squared minus 4x squared plus 12x. Let's combine like terms, and let's move everything over to the right side of the equation, leaving 0 on the left side. So this becomes a 4x squared. Combining these two, subtract 6x from 12x, we get a positive 6x. Subtract 18 to move it over, and now this equation is equal to 0. Let's make it a little simpler by dividing everything in the equation by 2. We end up with 2x squared plus 3x minus 9. This can be factored into 2x times x here, 3, that's 6 and 3, a positive 6, and a -3 will end up giving us the 3 that we need. And let's make mini equations with our two factors, giving two potential solutions. 3/2 is one of them, And with the other mini equation, we get -3 as the other potential solution. But we should remember that was excluded from the very beginning, so it cannot possibly be a solution since it makes a denominator equal to 0. That only leaves 3/2 as a possible solution. Just in the interest of time, I will tell you that when you plug 3/2 in for x and test this equation, it is a valid solution. So out of the two potential answers we got, 3/2 is the only valid solution. That's it for today's lecture, boys and girls. Fractions speak louder than nerds, and don't you forget it. God bless you.